what we're going to start with this chapter is with a topic called kinetics. Now, this is going to be a bit different than what we've done so far in chemistry, specifically in how we're going to be thinking about the reactions that we're looking at. Every chapter up until now, what we've been asking ourselves is what happens when this reaction gets to its end point or when it's done. However, there's a lot of interest for as a chemist of, well, how fast is it? What happens in the middle when it's not done, but maybe it's only been 100 seconds? I may want to answer questions about that. So that's what this chapter is going to look at. Instead of looking towards the end of the reaction, it's going to say things like, how fast is it? We call this study chemical kinetics. So chemical kinetics studies the rate of chemical reactions is what we're going to look at. And by reaction rate, what we mean is we mean the speed of a reaction. So how fast do reactants turn into products? So that's really what we're looking at in this chapter. So you can think of this kind of like something you might know, like, for example, how fast a car goes. If I think of my car as going 55 miles per hour, I may be going 200 miles, but if I stop after an hour, I've only traveled 55 miles. Similarly, a chemical reaction may eventually produce, let's say, a mole of a product. But if you stop it 30 seconds in, or you look at see how it's going, it might only have 1/10 of a mole. So that's what we're going to look at here. How quickly does our reaction go? So the way we do this is we talk about the rate. And by rate, we're going to mean the change in something. And I'm going to talk specifically, I'm going to give an example. Let's say we have a reaction that uses up iodine. We want to know about its change with respect to time. So this is for the reaction hydrogen plus iodine forms 2HI. So for that reaction, we're going to use up iodine over time. I also put a negative sign in front of here. There won't always be a negative, but since this is a reactant that's being used up, I expect it to go down over time, so the concentration should fall. Falling is represented with our negative sign. So now, how do I actually write this? What does this look like? This is rate. So if I want to know what this is, then I'm going to get a negative. I'm going to take I2 at its final time. So we're going to say 2. So we're going to say like T1 equals start, T2 equals point we're interested in. So it's not the end of the reaction, but it's somewhere after the start of it. And point 1, I just realized, point we're interested in. This doesn't have to be the start. It could just be an earlier time than T2, though. That's what's important. So it could be that we're looking from the start to 100 seconds, but we could also be interested between 50 and 100 or something like that. So you could pick any time you want. So to be clear, while in this case I'm going to talk about it from the perspective of the start, we could just be saying in general, oh, how fast does this reaction go when you compare at 50 seconds to 100 seconds? So you have I2 at the time 2 minus the concentration at time 1. And we'll divide it by time at 2 minus time at 1. So for an example, let's go to another slide. So let's say we have a chart of I2 concentrations and time in seconds. This is in molar. So let's say we have this table. We have 0 seconds, we have 50 seconds, we have 100 seconds. Now, no, I'm making these numbers up. It would depend on the temperature, how fast this would change. So you'll get different numbers at different places. But let's say it started off at 1 molar. Let's say here it's at 0.90 molar. And let's say here it's at 0.81 molar. So what we've seen is we can now ask a question. For example, I could ask, what is the rate of change when you're looking from 0 to 100 seconds? So then I'm going to look at the change in I. So this part is going to be, well, at 100 seconds, so this is for 0 to 100 seconds. So 100 seconds, we've got 0.81 molar minus 0 seconds, 1.00 molar. Then the time, we have 100 seconds minus 0 seconds. So that's going to give us some values. Let's put those in. Divide by 100. And I'm going to get negative 0.0019 molar per second. Or we could say 1.9, negative 1.9, times 10 to the negative 3 molar per second. Those are both true statements, and they're both fine. Note that the unit for these is many times in molar per seconds. We'll be looking at compounds where we're interested in their molarity is how we're reporting how it changes. So this is the rate at which that changes from 0 to 100 seconds. However, this, for many reactions, not all, we'll talk about some where this doesn't happen, but for many reactions, the rate at which it goes down changes based on how much you have at any particular time. So the rate isn't a constant. So let's just look at 0 to 50 seconds in this example. Or let's look 50 to 100 to show you how to do it if the time doesn't start at 0. So then we're going to look at this. So at 100 seconds, it's still 0.81 molar, but now we're at 0.90 molar for 90. Or for 50 seconds. Similarly down here, we still have 100 seconds as our ending point, but now we're 50 seconds is that point. So this time we get 0.81 minus 0.9 divided by 50. To put that. And this time, for this rate from 50 to 100 seconds, it's negative 0.0018 molar per second. So it is dependent on what time frame you look at your reaction, what the rate's going to be in many instances. So this is something we will have to specify for you. We'll say, hey, this is the time frame we're looking at. Let's talk about the concentration of this thing there. Now, what does this look like, graphically speaking? So this is a good representation of this. So for example, this one's looking at H2. Let's say H2 started at 1 molar. As our concentration goes down for hydrogen, so you'll notice this is going down, our HI is simultaneously going up. And it's not just that one is going down and the other is going up, but they have a relationship between them. So looking at the balanced chemical reaction here, so if we look at this, every time you use up a hydrogen molecule, you make 2 HI molecules. So if you used up 0.1 molar hydrogen, you should have 0.2 molar HI made. So this relationship holds for the entire reaction. And you'll notice the hydrogen, over time, it goes down slower and slower. Like when you get towards the bottom, these points down here, there's not as much distance every 10 seconds. See how it's falling slower? Like right here, over 20 seconds, it didn't even fall at 0.1 molar. But at the beginning, over 10 seconds, from 0 to 10, it dropped from 1 to 0.8. So as you're running out of reactants, the reaction's getting slower. And this isn't true for all reactions again, but this is true for many. And the idea being is that let's say the reaction involves, well, the molecules have to be present. They have to be able to find another iodine molecule to react with. So if you have fewer hydrogens, they can't find iodines as often because they're going to have to successfully collide into each other to make this new reaction, this new molecule, this HI. So if you have fewer hydrogen molecules or fewer iodine molecules, they're less likely to find each other. So they're going to have less chances to react and form this new molecule HI. So as their concentration goes down, they're not going to make as many products. So how do we then take that relationship, which is shown graphically here? How are we going to take that into a mathematical relationship? So this is a general rule. So first, let me show you what this... So this is suggesting that A and B are reactants. And so this is for this equation specifically. So this is little a is a coefficient in front of big A plus little b in front of whatever compound big B represents reacts to form little c, whatever C represents, plus little d, whatever D represents. And these are either going to be gaseous or aqueous since we have molarities. We can do this with any particular reaction. So let's try it with the H2 plus I2 goes to 2HI reaction we were looking at just a moment ago. Let me check something. Making sure they were all gaseous. I was pretty sure they were. So for this reaction, what that means is our rate of the overall for the reaction is equal to the negative of, well, there's no number in front of hydrogen. That means that it's a 1. So 1 over A is 1 over 1 here. So this is just negative 1 times the change in hydrogen over the change in time is equal to the negative, again, iodine just has a 1 in front of it, so it's going to be negative change in iodine over change in time is equal to, and then we have the HI one. So this one now there's a 2, but it's on the product side, so it's got a plus in front of it rather than a minus. So it's 1/2 the change in HI over change in time. So what this means is if you know any one rate, you can compare it to all the others, as well as the overall rate of the reaction. For example here, let's say someone went ahead and told you, oh, we know the change in hydrogen. We measured it. The change in hydrogen for this reaction at the time we're interested in is 0.050 molar per second. Well, then I can plug it into this equation and I can solve for any other one. For example, let's say I wanted to know HI's rate now. Well, what we know, let me make me disappear so I don't block the way. So what we know is that the negative of, oh sorry, this should be a negative by the hydrogen as well, because we're losing it, it's going down. So the negative of hydrogen with respect to time is equal to a positive 1/2 of the change in HI over the change in time. So now we just plug in this value. So we have a negative 0.050 molar per second is equal to 1/2 of the HI that we're interested in. Well, now I'm going to multiply. First, these negatives are going to cancel, give me a positive. I'm going to multiply both sides by 2 to get rid of this fraction here. So that's going to tell me that I should have given myself more room to write it, but also that my change in HI with respect to time at this time frame is going to be 0.100 molar per second. That's because I multiplied by that 2. This also matches conceptually what we said on the last slide. I expect that HI should go up twice as fast as the hydrogen went down. And that's what's happening here. The hydrogen goes down at a rate of 0.05. The HI grows at a rate of 0.1. So my hydrogen iodide is growing twice as fast per second. Now for the rate of the overall reaction, I could plug it in, and we have this relationship here related to hydrogen. So in this case, I would just multiply this by -1, and I would get for the overall reaction, again, I should have given myself more space. So the rate of the overall reaction is going to be 0.050 molar per second. So what that means is this entire reaction here happens such that if you take 1 second, 0.050 molar of this reaction is going to react. So we can change that for any particular one. That means the reactants are going to go down by 0.05 because they have a 1 coefficient in front of it. And the product, well, it's going to go up twice as fast as the overall rate. It's going to go up by 0.1. If we had a 3 in something, it would go up at the rate of 0.15. If that 3 was on a reactant, it would go down at the rate of 0.15. What's nice about this is you can take any particular reactant or product that you know and use that to solve for any of the other ones here. So that's how we're going to solve problems in this area. So let's take a look at an example. So we have hydrogen peroxide plus 3 of this I- ion plus 2H plus are going to react to form I3- and 2 water molecules. So in the first 10 seconds of the reaction, we're told the concentration of I- drops from 1.0 molar to 0.758 molar. This will many times be reported in a table. So you might have a table that looks like this. You have I-, and then you'd have time. And time could be on a different, and then you would have, oh, that's it. I- and time. So you would have 0 seconds, 10 seconds, and this would be 1.000 molar and 0.758 molar. And they'd likely actually put the molar up here, and they'd probably put the seconds up at the time. And you might get a table with lots of them if they're going to report multiples. So now, for step A, what that means is if I want the change in I with respect to time, then I need to take my 0.758 molar minus my 1 molar and divide it by 10 seconds minus 0 seconds. So let's see what that gets me. 0.758 minus 1 divided by 10. this is going to give me negative 0.0242 molar per second. Now, the question also asks me to determine the change in H plus in that time. So what we need to do is we need to set up our relationship between these two using that equation. I'm going to go back for a second. So using this general equation of negative 1 over A equals negative 1 over B, so that's for the reactants, and then positive for the products. So I minus is a reactant. H plus is a reactant. That means both of them are going to be negative. I'll bring mine. Okay. So both are going to be negative. So let's make them equal to each other. So we have negative 1/3 of the change in I minus, because there's a 3 coefficient in front of it, is equal to a negative 1/2 times the change in H plus. So now we take this value we found in part A and we plug it in there. So we have negative 1/3 times negative 0.0242 molar per second is equal to negative 1/2. And if you went ahead and multiplied by 2, that would be fine as well. But I'm just going to do this. 0.0242. So I now have, start a second line. I've got negative times negative is positive. So I have 8.07 times 10 to the negative 3 molar per second is equal to negative 1/2 of my change in H plus over my change in time. So now I multiply both sides by negative 2. So I'm going to multiply both by negative 2. That'll get rid of this fraction. So when I do that, I'm then going to have negative 1.61 times 10 to the negative second molar per second is my rate of change for my H plus. And that is what we were looking for. So that will answer part B. So hopefully you can see how we're able to connect these different rates of reaction to each other. So in terms of what we're actually I'm sorry, my face. There you go. In terms of actually doing this, so in a lab, for example, what you're going to have to do is we'll have to connect somehow some piece of information to the concentration to be able to measure it over time. For example, in one of the labs we tend to do in our class is we're going to do something where we look at a solution that has a color to it in one form, but the other form is colorless. And what that means then is you can look at how much color is present by shooting a light through the substance. And when it's colored, it's going to block the light. It's going to become absorbed. And by watching the change in the amount of light being absorbed as we shoot it through a sample over time, we can use that to monitor the concentration changing. So as the solution becomes darker, that can either represent a product forming, or it could represent, or if it was a reactant that was colored, it would become less dark because then the reactant would disappear. So by watching that change in either becoming darker or becoming less dark and monitoring it with something so that it's not just my eyeball noticed it was dark or not, but instead we measured it with a tool, with something that could measure the amount of light being absorbed, we can use that to figure out how much the concentration changes. So that's by far one of the more common ways, and that's how we're going to do it in our own labs. We're going to see how fast something is changing. So with that, this is how we're going to talk about rate. What we'll be doing in our next video is we'll start talking a more general case of a rate law. So far, everything we've talked about is what happens in a very specific time frame. But I'm going to want an equation for what do I do if I want to know any particular time. Like I want to say at 47 seconds what's happened. Well, we'll need to set up a set of rules to be able to work with situations like that. And that's what we'll do next.